inviting me to this great workshop. And I would also like to thank the audience for your patience. It's a little bit elementary stuff. So anyway, let's make a start. So I will talk about the m steps of a mono-anabelian geometry of number fields. First, I would like to introduce some basic backgrounds. The very first result in anabelian geometry for number fields is the famous Noguchi-Uchida theorem, which basically says that if you have two isomorphic, if you have number fields who has isomorphic absolute Galois groups, then this isomorphism of absolute Galois groups necessarily arises from field isomorphisms, and also in a functorial way. So this is the first result in anabelian geometry, essentially. And then in 1970s, Uchida improved this theorem by only considering their maximal pro-solvable quotients. The proof was actually very much the same as the original one, but it's a big improvement. But later, maybe a few years ago, Saida Tamagawa greatly improved Uchida's improvement by restricting finite degree of solvability. So this theorem basically asserts that if we have an isomorphism between m+3 step solvable Galois groups of number fields, maybe I should explain what does it mean by m+3 step solvable. Stop here. So very quickly. So if we have G a profinite group and I be a non-negative integer, we write G bracket I to be the closure, maybe the closure of ith derived subgroup. And we write G superscript I to be the quotient. And this is called the maximal I-step solvable quotient. And when I is equal to 1, it is in particular the abelianization. So I have to go back to the share. Yeah. So Saida Tamagawa's theorem essentially tells you that at the cost of 3 steps, we have an abelian result in a functorial way. Also, they have also proved that if we ignore functoriality, then we need only 2 steps. Your latest result, meta-abelian one. I guess that is not functorial, right? It is functorial. Oh, that's even functorial. Oh, amazing, because in this paper, your theorem 2 isn't functorial. Yeah. In this paper, you only prove for 3, and that result isn't functorial. Yeah. Anyway, so let's continue. Yeah, but neither the results above are explicit reconstructions to the fields from Galois groups. So basically, both results, we basically start with an isomorphism between Galois groups, and we obtain isomorphism of fields. So it is not group theoretic reconstruction. And one naive way to generalize this sort of result is by, say, we are assuming both fields are number fields in this result. And probably we may generalize that, well, what if we only assume one of them is a number field? What will happen? What will happen is the result fails. So this sort of result, the Noguchi-Uchida type result, is actually quite rigid. It requires us to know where does this groups come from. It must come from an automorphism group of some solvable closure or m-step solvable closure of number fields. It cannot come from other places. On the other hand, there is a result proven by Hoshi like several years ago, asserts that, well, if we have a profinite group isomorphic to the maximal prosolvable quotient of some Galois group of number fields, then there exists a group theoretic functorial reconstruction to the solvable closure. And of course, the base field of the number field, which is isomorphic to our number field. And this sort of result that we're starting with, here we only require G to be an abstract profinite group, but not a Galois group or distinguished quotient of GK. So we only need abstract profinite group. So we do not care about where does it come from, but we still obtain this reconstruction. We still obtain information about our number field. So this is a quite surprising result. Yeah, because this. Yeah. Of course, isomorphic too, but we do not require that G is. We do not require what isomorphism it is. We just need to require it is an abstract isomorphism. So this is somehow a surprising result. This sort of result is kind of rare and very strong. And then one of the main theorem of my talk, which is a joint work from me and Mohammed, is the m-step solvable version of Hoshi's reconstruction. So for technical reason, we need to assume that M is at least 2. So if we have an abstract profinite group G isomorphic to GKM plus 6, I will explain later where does this plus 6 come from. For some number field K, we can group theoretically reconstruct a field FMGM, which is essentially the maximal m-step solvable extension of K, and together with the G action, of course. Without this, we cannot recover the base field. And the base field FGM, which is essentially isomorphic to K in a functorial way. This is a main result, one of the main results of this talk. And yeah.
In the third line,
yeah.
FMG.
Yeah.
Selected field is not FMG, but FMGM plus 6.
Yes, but yeah, but this I just want because the action of course arises from G. This is for sure, but I just want to make this looks better. Yeah. The input is actually G. So if we think the G is isomorphic to GKM plus 6. So it is essentially the input data is G, but I just want to make sure that this actually this looks better because I mean this is just notational stuff. So I should mention that both Hoshi's result and our result actually do use the bi-anabelian results, the Nuki-Uchida or Sadi Tamagawa. We use the statement of such theorems in an essential way. So in particular, our results won't provide alternative proof to the bi-anabelian result. And there is another bonus result, theorem 2. Basically, this is a special case of theorem 1, but not quite because the proofs are different. Suppose G is a profinite group isomorphic to GK3, the maximal 3-step solvable quotient, where K is an imaginary quadratic, or K is Q. Then there is a group theoretic reconstruction to K. And this reconstruction, surprising, maybe not so surprising, this reconstruction is independent from the bi-anabelian result. So essentially, this result gave an alternative proof to the bi-anabelian result, but only for imaginary quadratic field or Q. Recently, I also discovered that an alternative way to prove this also for real quadratic fields, but I will leave that to the end. So maybe I should explain how does the proof work.
And also, you don't need GK6, but GK3 is enough.
Yeah, but only for imaginary quadratic fields and Q. Two proofs are quite different. This and this are completely different proofs. So here's the structure of proof of theorem 1. I hope I can use the screen and whiteboard simultaneously, but I will go to whiteboard. Yeah. Oh. Can I erase this? I guess I can. So first, I'm going to explain where does the 6 extra steps come from. So consider a number field K, and its maximal m plus 6 step solvable extension. So this part is GKM plus 6, and the maximal m plus 3 step solvable extension. Okay, so this part is isomorphic to GKM plus 3. And we take an open subgroup H of GKM plus 3. This would correspond to a finite extension L of K contained in Km plus 3. In other words, L is solvable over K of length at most m plus 3. And we consider the inverse image of H in GKM plus 6. We will denote this by H tilde. And it turns out that, the maximal 3-step solvable extension of L is contained in Km plus 6. And this part is actually isomorphic to the maximal 3-step solvable quotient of H tilde. And hence, H tilde 3, 3-step solvable quotient, is isomorphic to GL3. And the 6 steps comes from, we need 1 step for this compatibility with taking open subgroup. And 2 steps come from the local theory I will introduce later, slightly later, 1 minute after that. And the extra 3 steps, so 3 steps is to use the main statement of Saito-Tamagawa's theorem, which we need to use actually for theorem 1. So this is where the m plus 6 steps come from, and this 6 extra step. At this moment, I don't know how to cut this 6 by some smaller integer, but it could be possible. So let's continue. So step 1 of the proof. So the first step is essentially a result by Saito-Tamagawa. So it's the this is so-called local theory. So essentially, local theory tells us that at the cost of 2 steps, we can recover decomposition groups. So if we start with GKM plus 2, there is a group theoretic reconstruction to the set of decomposition groups at the level of GKM. I will denote by decomposition tilde, which is decomposition subgroups. Of GKM at non-Archimedean primes. And this reconstruction is entirely functorial and group theoretic. So we can actually use this in our reconstruction. So in other words, if we have a our G, which is isomorphic to or G, which is isomorphic to GKM plus 6, there is a group theoretic reconstruction to the set of decomposition groups, but in a group theoretic way, we cannot say it fixes primes because we don't know field theoretic information. Yeah, so we will write G M plus 3. But actually M plus 4 is also okay, but we only need M plus 3. It's group theoretic reconstruction. And take an open subgroup H open in Gm plus 3. By this relation, we have H tilde 3 recovers the set of decomposition subgroups of H1. So they are just abelianizations of local Galois groups, isomorphic to them. H tilde 1. So they're just abelian ones. And for the notation, I will write without tilde decomposition, Gm plus 3 is defined to be the orbit of this Gm plus 3 set. The action is given by conjugation. So decomposition Gm plus 3 modulo the action of Gm plus 3 by conjugation. And with this local Galois groups, they are isomorphic to local Galois groups by Galois 1 or something. So with this local Galois groups, we can recover various local invariants using class field theory also. So we take D, be a candidate of decomposition subgroups in M plus 3. Then by consider the structure of DF, which is known by using local class field theory, we obtain the following invariants, like PD is the residue characteristic, and we also use DD, which is the degree, the absolute degree. And probably FD, we also use, is the inertia degree. And we also need to use we can recover the inertia subgroup and the wild inertia subgroup. And Frobenius automorphism, which lies in the unramified quotient. Frob out. And hence we can recover the multiplicative group and the unit group. And finally, the roots of unity contained in the maximum m-step solvable extension of the completion. So maybe I should write non-canonical isomorphism to cumul Z. And the important notion is called the cyclotone. The cyclotone, which is defined to be the inverse limit of the n torsion part of mu d. So it is isomorphic to Z1, the Tate module, full Tate module of GM. So all this can be recovered from D, possibly also the image of D, the pre-image of D in the decomposition group of GM+4. But all these are group theoretic and only uses local class field theory.
Not only the local theory, but also like group band type result.
Yeah. Without group dot one, we don't know this is actually local Galois group. Yeah, and this is step one. This is.
How do you have to reconstruct mu D?
Sorry.
How to reconstruct mu D?
Mu D.
Mu D is not the torsion of K cross D, but the large X. So how do you reconstruct mu D? What's the torsion points?
Yeah, torsion points of
extensions.
Yeah, of Km, of KMD, and we take inductive limit on open subgroups of this notion, and we just take torsion subgroup, which is this. Yeah, and this is end of step one. Wild inertia. Wild inertia group, which is the propicilo of the inertia subgroup. Step two. I will stick with this board. And step two, we prove a central theorem called local global synchronization, which is this step. I don't know if Sujimura-san can see this, but it's okay. So step two, I would say local global.
I can see. Thank you.
Oh, that's good. So local global synchronization. And Kummer containers. So the local global synchronization basically tells you that the global cyclotomic character comes from the local ones. And the Kummer container, such container is quite common in mono-anabelian geometry because sometimes, maybe most of the times, we cannot reconstruct things directly, but we can reconstruct something larger, the containers. And then we do all the constructions within the containers. And this is the Kummer containers, is the container we are going to do our reconstructions in. So there are actually two ways to recover the global cyclotome. I will use something different from my thesis. So actually, this is a direct application of Saidi Tamagawa's theorem of reconstructing cyclotomic characters. So maybe I should this theorem. Saidi Tamagawa. So there exists a group theoretic reconstruction. To the cyclotomic character. Maybe GK3, Z hat, chi K from GK3. So this means you need only 2 steps more to recover the cyclotome. The cyclotome is Z hat 1. And in the reconstruction is listed in their proof. The proof essentially tells you that you can recover ZP1. And if you recover ZP1, you recover the P part of the cyclotome, and you product all P. So you obtain the reconstruction of the cyclotome. So this implies that
There is a big difference between the reconstruction of character and the reconstruction of J hat 1.
Yes, but in their proof, they prove that you can actually recover ZP1.
But this statement tells us that. So just
maybe I should say the proof implies. The proof of this implies. Yeah. Actually, the proof implies that there is a group theoretic reconstruction of the cyclotome lambda G. This is also notational stuff, but it is m+3, but it really doesn't matter because they are all isomorphic to Z1. So we can group theoretically recover the global cyclotome.
It's, for example, in the case of what is mu d?
Yeah.
This is inductive, okay, not complicated. Okay, K cross D point. This is a subgroup of the hybridization of D.
Yeah.
So this is having natural continuum. So lambda G 3, so I'm sorry, I couldn't read.
M+3, sorry.
So what does this mean?
Probably it should be written as lambda G, but
Subquotient of G or?
no, this is the global cyclotome. This is just Z1. Yeah. So
just so okay. It's dependent on your next argument.
Okay. So this is the global cyclotome. So the local global synchronization. This basically asserts that if we have a decomposition group D in Gm+3, then there is a D equivariant. The variant isomorphism goes from lambda D to lambda G. So this is the statement of local global synchronization, which is also a direct consequence of Sadi-Tamagawa's theorem. At the first glance, this might be somehow trivial, which somehow, unfortunately, is the case. It is quite simple. But I would mention the home version of this synchronization. So this is actually a conjecture. Yeah. Somehow, yes.
Yes, but so I mean, so this is not canonical.
This is a canonical. This is canonical.
I mean, it depends on how the issue of how to reconstruct lambda G, of course. Because if you have an abstract cyclotome, then such an isomorphism always has a possibility of G hat cross ambiguity.
Yeah.
So in order to obtain the canonical isomorphism, we have to specify how to reconstruct lambda G, of course. But you mean that we can do that?
Yeah.
Okay.
Yeah, of course we can.
Yeah, maybe this is not very precise. So you said that you put this argument, you change. So what you are presenting is an argument which is different from the argument in your thesis.
Yeah.
I think the argument in your thesis is more correct.
Yeah, but I think this should also work.
Right. You have to precise.
I'm afraid that in the joint work of Mohammed and myself, we can only reconstruct the cyclic character, not the cyclotome. And so that we patch the cyclotome character, but not the cyclotome itself. And also that it is difficult to compare some piece of the cyclotome and local cyclotome. So I'm not so sure, but the proof does not give rise to the cyclotome. So the cyclotome character.
Yeah, then I will introduce the notion in my thesis. Okay. Yeah, because the original version is very lengthy. Yeah. So I also want to mention a conjecture, which is a home version of home version of microglobal synchronization. So the home version is maybe I will use full Galois groups here, but the M-step solvable version are actually quite similar. So let GK to GL be an open homomorphism. Then there exists, maybe say alpha, exists an alpha equivariant isomorphism between their cyclotomes. We say alpha star, lambda GK to lambda GL. This is highly non-trivial. Essentially, if you prove this, you prove the home conjecture of number fields, which is unfortunately quite open. So our case is somehow trivial, but the home conjecture is highly non-trivial. Anyway, let's continue. Yeah, this implies the home form, but you cannot prove this. Yeah. Also, me and Mohammed also proved the M-step solvable version of this. Implies the geometricity of morphism of Galois groups, but still, there is no proof to this. So the next step is the Kummer container. So we need to introduce some field theoretic version first. So K be a number field. And the Kummer container will denote by script H cross K is defined to be the fiber product of the following diagram. So this is the Kummer completion, which is defined to be the inverse limit of K cross modulo K cross to the nth power. Injects into the product of all. Here, this script PK thing is the set of finite places of K. This is KP cross hat. The hat are the same, so this is also the Kummer completion, the inverse limit of K cross modulo K cross to the nth power. And have the group of finite idels, which is the restricted direct product of K cross times, KP cross times OP cross. So the Kummer container is the fiber product of this diagram. And we also define the lower cross K, H lower cross K, is H upper cross K, adjoining a distinguished zero. So this becomes a monoid. It's no longer an abelian group. This is an abelian group. And what we are going to do is we are going to recover H cross K from G. How to do this? We need to recover all these objects. And this part is okay, because we have already recovered the local multiplicative group. And this part is also okay, because we have also recovered local unit group. So this is just a restricted direct product. And this part is somehow problematic. Of course, this arises from Kummer theory, But the problem is we have this is mu n goes from km cross to km cross nth power. And this sequence is not right exact for any m. So, but it turns out that this is okay. We can also reconstruct this by using the following lemma. So this is a crucial lemma. So let K be of characteristic 0. Be a field of card 0. Then there exists a canonical isomorphism. Goes from H1 GK mu n to H1 GKM mu n. For any m bigger than or equal to 2. So this is the key reason why we need to assume m is at least 2 in our reconstruction. So these two cohomology groups are canonically isomorphic. The proof is actually quite simple. It's just an immediate consequence of inflation restriction sequence. Then we can reconstruct our K cross hat group theoretically. So K cross hat, maybe not defined with, but I don't know. It's isomorphic to H1, maybe Gm plus 3, lambda Gm plus 3. So the next job is to define the Kummer container group theoretically from G. And the tricky thing is we cannot just put everything inside this diagram because these maps are not compatible. We need to specify these maps in a group theoretic sense. So we have H1 Gm plus 3, lambda Gm plus 3 here. And of course, this is injective, but I will specify later what this map is. And we have P lies in decomposition G m plus 3. So this is really just primes, the equivalence class of the orbit of the set of decomposition groups. So H1 D. Oh, sorry. Oh, it's not this. Oh, so this is in decomposition Gm plus 3. This is just Kp cross hat. So this is just the same thing as K cross D, but D is a candidate of P, and they are all canonically isomorphic. So we just write K cross P. And here we have I fin Gm plus 3. So as I mentioned, we can recover the group of finite idles from Gm plus 3.
I should ask you how to define the row.
Yeah, that's what I'm going to say now. So this map is fairly canonical because we can just consider the these are just dpabs by the fact that dab is isomorphic to H1 d lambda d. And these are just natural inclusions component-wise, because whenever you have the component, whenever it is OP cross or it is KP cross, they all injects into K cross P hat. And this one is slightly more trickier. First, we need to consider what to say. So we need to consider the following map: H1 G plus 3 D G n plus 3. This injects into reaches P decomposition G n plus 3. But also we need to consider the choose for each P we choose a candidate D. This is injects into D lambda D. So this inclusion basically follows from Tate duality. And then this is isomorphic to this component-wise. So this inclusion can be viewed as this composite.
How to define the isomorphism of H1?
Defining this isomorphism, I see what you mean. So this is by taking the cohomology to the sequence, the exact same question in the Viva. Yeah. So to the sequence. So this is mu d and torsion part to k cross d m to k cross d m. This is nth power. We just take the cohomology of d to this sequence, and we use this lemma. We obtain a canonical isomorphism component-wise. Yeah. So from this point of view, we have recovered the group theoretic version of Kummer container, and we will denote it by H cross G m plus 3. This m plus 3 means we recover it from G, but at a cost of 3 steps. Also, the lower cross one just adjoining a distinguished 0. Actually, we do not need to. We do not need 3 steps. We only need 2 steps. But for the sake of consistency, we write m plus 3. And using the exact same way, we can recover. So let H be an open subgroup. Gm plus 3 open. And we record the notion H tilde is the inverse image of H in G, and we consider its maximal 3-step solvable quotient. This is isomorphic to GL3 for some L. And we apply the same thing. As I mentioned, it actually requires only 2 steps. So we can also recover the Kummer container associated to. This is also a strange notion. Forgive me for abusing the notion H, but essentially it's H tilde. But I will write it as H, and of course the lower cross one.
So this was very technical, so you can ignore or omit.
Yeah.
I want to ask you. In this situation, you have a H tilde 3.
Yeah.
So you have a take neuron H1.
Sorry.
It's a decomposition subgroup of H.
H1, yeah.
So you have just an abelian notation of D.
Yeah.
It's difficult to find, for instance, I or K cross or.
But actually, this can be done. It's a little bit technical.
So if you have a abelian notation,
Yes.
then you can reconstruct everything.
Possibly together with some because we allow one more steps. We allow one more step. We are starting from GKN plus 6. So actually, we can consider the image of abelianization in something like
You don't start with the open subgroup of GM plus 3, GM plus 4? No. GM plus 2 or I don't know. If you start with GM plus 3, then you only have.
I understand your question. I understand your question.
We couldn't have a mu or lambda.
Yes, I know, because we need compatibility.
Not this, but maybe you can of course modify or you can. But so this is not correct for me, I think.
Yeah, I see. Because at this stage we only have abelianized decomposition group, and abelianized won't work.
But maybe so you can modify just m plus 3 or m plus 2.
Yeah, the thing is, we can recover this. We can recover this for H, and also we can recover this for H, and then we can recover this. So we do not. I don't think I have used because when I recover the global cyclotron associated to H, I do not obtain from. It's not from the local one, if I remember correctly. I use a slightly different way to define it, so that I avoid this because I'm aware of this also.
Similar to the case of G, but not the same.
Yeah, slightly different. Sorry, I can't remember the details at this moment, but it will work. It will work. So the next step. This is step 3. Step 3. We're going to reconstruct Qm plus 3 inside Km plus 3 group theoretically. This is somehow the central step of the reconstruction. It seems that I don't have enough time. I will go quickly now. So for each n, we define the following two sets, subset of the Kummer container. So we write script GF1. Maybe I should define inductively. This is the set of roots of unity. Oh, yeah, is equal to 1. But this is also contained, and nth root of unity contained in the Kummer container. Cross K. And we write F. Oh, this is K. To be the field extension generated by by GK1. And we do this inductively. So for an arbitrary n, and this 2, this is n is equal to 1. So script gkn is defined to be the nth power in the previous field, n minus 1. And fkn is a field extension generated by gkn and fkn minus 1. And it turns out that F1 is just the maximum abelian extension of Q, and FKN is the maximal n-step solvable extension over Q.
Maybe you have to change second line and third line. The second line you write
Yeah.
But so xn is n's power of x is equal to 1. You write.
Sorry. Well,
in the third line you wrote x in x is equal to 1. Sorry, third line 1, 2, 3.
Yeah.
It is not third.
I see. Maybe you should M, right? Yeah. So from this construction, we can. The point is, this Fk and Gk can be recovered group theoretically, because it is a subset of H cross. Maybe this is not H cross K. It's H cross L, the inductive limit of L, where L ranges over all finite extension of K inside Kn plus 3. So as the inductive limit. So they are all contained in inductive limit of H cross L. This is actually not entirely trivial. This follows from a lemma by Hoshi. So the point is, we have Fk m plus 3, or maybe in my paper it was m plus 4, is equal to Qm plus 3. And on the other hand, this Fkm plus 3 can be recovered group theoretically because everything lies inside the Kummer container. The Kummer container can be recovered group theoretically.
How to reconstruct the field extension generated by the field structure is not reconstructed.
Yes. But on the other hand, this is also a product of it turns out to be a subring of product of fields, and the field structure inherited from the product of fields is inherited from the ring structure. And
How to reconstruct the field structure of local fields?
That is one of the most technical part of the proof.
But this is a field case. This is not a group theory.
Yeah.
But he stated that it is.
It can be done, but we need more steps. We need more stuff. So that is one of the most technical part of the proof. Unfortunately, I cannot go to very much detail. I don't have time. So one has to from G, we can recover the maximal n plus 3 step solvable extension of the completions if the degree D is equal to 1. We can recover all these fields. The technique is somehow very similar to Hoshi has proved. Hoshi proved that if you have a solvable Galois group, solvably closed Galois group, you can recover locally all the algebraic closures of the completions. The proof is actually the same, but only works for D equal to 1 in the M-step solvable case, because in the M-step solvable case, if D is not 1, then this thing is different from QPM plus 3. But in Hoshi's case, QP bar everything is equal to QP bar. So In Horsey's case, he can recover everything. So, but in our case, we only need to, we can only use degree 1 decomposition groups and degree 1 primes. And using this, we have field structure on this, inherited from the product of fields. And next, next is also an extremely technical step called standard type subfields. I guess. Yeah, I should conclude. I don't have time. Yeah, but I should briefly explain. So these are just isomorphic pairs of our number field and its maximum M-step solvable extensions, but equipped with an injection into the local fields and the local M-step solvable extensions. And it turns out that such pairs can be recovered group theoretically. And this is very technical, actually. And using this, we can recover. And at this step, we use the main statement of Sadi-Tamagawa. So using this, we can recover the number field with respect to the action of G rather than the action of D by considering the product and the kind of the diagonal of the product of the standard pair subfields together with the isomorphism obtained by Sadi-Tamagawa's theorem. So we obtained the final reconstruction. And I should briefly mention theorem 2. Theorem 2 is very easy. I should mention it will be very quick. So theorem 2 is somehow very easy. So we need 2 steps to recover the Kummer containers. So once we have recovered the Kummer container, we can recover something called NF monoid, which is basically an analog of the data that you use to prove Uchida's lemma in the function field case. So basically, we need multiplicative group, we need local stuff, and we can recover the additive structure. This is actually using Horsey's lemma. Horsey proved the number field case for the Uchida's lemma. And this is theorem 2. But theorem 2 only works for imaginary quadratic fields, or Q, because only in this case we can recover the multiplicative group. In general, we cannot recover the multiplicative group. I guess I will stop here. Thank you.